Hello everyone. In this video we'll be discussing mathematical statements. And the first thing I want to talk about now are logic symbols or logical symbols. We have 5 symbols here. There is and, or, if, then, if and only if, and not. So these P and Qs here are assumed to be statements. They could be mathematical statements as far as like equality, like these we have here. They could be a sentence like the president is Joe Biden or something like that. It could be a true statement, it could be a false statement. So P and Q could be statements that are either true or false, it kind of depends. Now, based on that, we'll actually see what these, I guess, combinations of statements using the symbols is, if that's true or false. And we'll discuss that in a moment. Before we get to that, I want to kind of describe here what these things mean. So this is known as a conjunction. This is known as a disjunction. This is an implication, or sometimes known as a conditional. This if and only if is biconditional. And this is a not, which is known as a negation, actually. So these are the actual names that I have here. Remember the actual names of these symbols. But what they really mean are and. Think of like this is like an A for and. This is or. So and or kind of like opposites. And this is if then. So the way you read this is if P then Q. And this is if and only if. And if and only if, by the way, basically means that if one is true, then the other is true and vice versa. So this means if P then Q, this means if P then Q and if Q then P as well. So it's two-way street here. And this is not. So I'll describe real quickly, verbally, when these statements are true. P and Q is true when P and Q are both true. So if one of them is false, or if they're both false, it's a false statement. If one of them is true, at least one of them is true for the or statement, then it is a true statement there. So P or Q is only true when either P or Q is true. If they're both false, it's false. If one of them is false, but the other one's true, it's still true. If P, then Q, that one's actually really hard to explain. But let me just say that false cannot imply truth. False can imply truth, like we'll see with this example. Truth cannot imply false, but false can imply false. And of course, truth can imply truth. So that takes a little bit of time to develop maybe, but that certainly is true there. And this statement here, let me just describe this in blue. I kind of mentioned this earlier, means this and, so let me write an and symbol, the other way around. So there's a biconditional statement. So this is the, I guess, converse of this statement. So if P then Q, that's a conditional statement. And Q then P, if Q then P, that's the converse of that statement. Okay. And then not P, again, is the negation of P. So it's just saying not something. So for example, if the statement is, I take the train every morning, not P is I don't take the train every morning. Something like that. So this statement is true when P is false. When P is false, not P is true. So it's kind of like the opposite. Okay. So now getting to this example, let's see, why is this true? Is this a true statement? Well, I'm saying it's true because if you think about it, if we call this statement P and this statement Q, really altogether this is the P, if P then Q statement. And I mentioned earlier, we know this is false and this is true. And can false imply truth? It can actually. But how is that? Doesn't make any sense because this isn't true, but that is. What does that mean? Well, I'll show with this specific example. Let me just say in general, the reasoning kind of depends. But the fact that this is true, we know that any false statement can imply a true statement. Or maybe it always does imply a true statement. So let me kind of demonstrate that here. If I were to, I'm just going to play around with this equality a bit here. So let me, I want to see what I can do. I can add 1 to both sides. I don't know if that's probably the best thing to do. Let's do this. I'll multiply both sides by 2. I think that works. So we multiply both sides by 2, we get 0 is equal to 2. And in fact, what that kind of tells us is that we can multiply both sides by any number and get 0 is equal to any number, actually. which seems like even more false, right? But in fact, because of that, we have so many options, we can prove true statements. So now if I subtract 1 from each side, again, -1 is equal to +1, and then if I square both sides, we get 1 is equal to 1, which is Q. So we get a true statement from a false statement. So it's possible to prove true things given false statements. And in fact, one can say, it's kind of a little bit of a stretch, but one can claim that given a false statement, you can prove anything, which I know sounds silly, but it kind of logically makes sense. In fact, there's a story of these two professors from some university having a discussion. I think one of them is a mathematician, the other one's a logician, which means they study logical statements like this. And the logician says, if you give me any false proof, or any false statement, I can prove anything. So the mathematician doesn't believe him or something like that. Maybe he's not a mathematician, I forget exactly. But he doesn't believe him and basically says, okay, assume that 3 equals 2 or something like that. I think it was like 4 equals 2. I think that works. Assume 4 equals 2 and prove that I'm the Queen of England or something like that. So the logician says, okay, 4 is equal to 2, divide by 2, you get 2 is equal to 1. So that means 2 people can be the same one person. So you and the Queen of England are 2 different people, but if 2 is equal to 1, you're the same person. So it's kind of an interesting thing. Like I said, it's a little bit of a stretch, but it kind of just shows that idea that false statements can imply true statements. Okay, so now I'm going to get on to the next kind of idea that will embody this a little bit, but then after that we'll discuss more new symbols and then move on from there. Okay, so in the last board we saw a lot of different logical symbols, and the big one we kind of been talking about was the implication symbol. P implies Q, or you can think of this as if P, then Q. Now something I did not mention is that these actually have names. P is called a hypothesis, and Q is called the conclusion. And usually what happens is you assume the hypothesis to be true, and you can deduce the conclusion to be true. So sometimes we'll actually use this idea when proving things directly. For example, mathematical statements you can actually prove. Here I have more of a logical statement. Maybe I'll actually in the next screen talk about one that's more mathematical. It'll be pretty simple actually, but get a little carried away. We'll see that afterwards. But now let's talk about these two new ideas, which are converse, which I spoke about a little bit in the last board, and contrapositive, which I have not spoken of yet. So converse is just taking the hypothesis and conclusion and swapping those. So it's saying if Q, then P. Now this is not always true. In fact, here's a classic example, which I'm kind of skipping contrapositive, we'll get back to that in a moment. So notice, P indeed implies Q. Since California is contained in the US, then if I live in California, then I must live in the US. So assuming I live in California, you can deduce that I live in the US. Because of that reasoning, California is contained in the US. So there's some logic there that we can deduce Q from assuming P being true. Okay, great. But notice that the converse is not necessarily true. Just because I live in the US doesn't necessarily mean I live in California. I can live in Idaho or something like that, right? But the contrapositive, actually, believe it or not, is always true if P and Q is true. Always true. Again, this is assuming the implication if P then Q is true. Okay, so how is that here? Well, let's kind of think about this for a second. So what is not Q implies not P? What does that mean? So this would mean if I don't live in the US, then I don't live in California. Now that makes a lot of sense, because since California is contained in the US, if I don't live in the US, how can I live in California? Because I'd have to live in the US in order to live in California. Okay, so that's kind of the idea behind this. Now it's a little hard to prove this without actually writing down all the possibilities, which would be known as a truth table, which I don't want to get too ahead of myself in, but maybe I'll just kind of show you a little bit of what's going on there. So here's the truth table. So we have P and Q. So different possibilities here. So P can be true or false, and Q can be also true or false. And the only total different combination possibilities are these four here. They're both true, P is true, Q is false. The opposite, right? P is false and Q is true, or they're both false. Now, this if P then Q statement is true, except for when you have false implies true. I'm sorry, true implies false, my mistake. Like we saw in the last video, I keep saying video. Like we saw in the last screen, the last board, false can imply truth, but truth cannot imply false. Well, we didn't actually show that, but that's kind of obvious, I think, if you think about it. Given true statements, you can't assume false things, or you can't prove false things, or else what you assumed was actually false to begin with. That kind of has to do with this a little bit, but so this is clearly the case. But now look, if we take a look at the nots of these, not P and not Q, well, they're just the negation. So when P is true, not P is false. And when P is false, not P is true. And similarly for Q, that would be false, that would be true, that would be false, and I guess that would be true. Okay. So now, what about not Q implies not P? When is this true? So let's think about this for a second. So we're saying that this would imply that. Now remember, false can imply truth, but truth cannot imply false. So this would be the only one that's false, and the rest would be true. That's how you kind of set up a truth table for conditionals. Okay. Now, the biggest takeaway here from me bringing up this truth table is that this right here and this right here coincide exactly. They're true when each of them are true. One's true when the other's true. One's false when the other's false. And also for the last two statements as well, the last two possibilities. So what this kind of says, these are equivalent statements. So you can always take the contrapositive of a implication and you'll get a true statement, an equivalent statement basically. Okay, so now let's take a look at an example like I kind of explained earlier where we'll actually prove a statement assuming P to be true. Okay, so here I have an example, like I mentioned, this is kind of a simple one. So we want to prove the statement, if A and B are even, then A plus B is also even. Now you can think about this and think of just any two random even numbers, and it's true that when you add them together, you get a result that is an even number. So just to kind of explain, based on what we've been discussing, this would be our hypothesis P, and this would be our conclusion Q. So to prove this statement, we're going to assume our hypothesis is true, and then we'll deduce that Q must also be true. Okay, so assuming A and B are both even, we can write them as 2 times something. So let's say A is 2 times K, and B is 2 times M. For some integers, or some numbers, K and M. Probably should mention this is a proof, so I should probably write that somewhere. Also, what's not mentioned here is that A and B are integers. So the reason why integers are kind of important in this case is because if it was just some random real number, then you don't have even or oddness. Doesn't make sense. Like 2.1 is neither even nor odd. Even or odd only applies to integers. 1, 2, 3, solid whole numbers basically. Okay, so for any integer A and any integer B, they're even if they're 2 times some other integer. That's literally the definition of being even. I mean, if you think about it, writing even numbers, you have 0, 2, 4, 6. These are the positive evens, and I guess 0, 2. They're all 2 times something. This is 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 2 times 6, and so on. So if you're even, you're 2 times something. So that's kind of like the definition of evenness. So all I'm doing is I'm using the definition of even, of being even so far, and then hopefully we can get to this conclusion here. So I'm going to now consider A plus B. I'm not assuming that A plus B is even, that's what we're trying to prove. But now we know, since A and B are even, we can write them as 2K plus 2M. And look at that, we can factor a 2 out, which is true because of distribution. If you distribute 2 back in, you get indeed this, so that's equivalent. And notice, since K and M are integers, their sum is also an integer, so we have actually shown that A plus B is 2 times the integer, which implies that A plus B is indeed even. And that completes the proof. So when you complete a proof, you usually write tombstone like this, or you can say QED, which is basically Latin for what has been asked to be shown has been shown, or demonstrated. There are other ways to say you're done, but I like the tombstone, it's pretty clean. Or a happy face, because I'm pretty happy we're done. So now I'm going to move on to the next idea, which will involve some new symbols, and then that'll basically be the end for the video. Okay, so now we'll take a look at what are called quantifiers, and there's 2 that I basically want to talk about. In reality, there's kind of more, which we'll get into in a little bit. But the main 2 I would like to discuss are what are known as existential, as in existence, existential, and universal. So the existential quantifier and the universal quantifier are basically shorthand for the sentences, or the, I guess, part of a statement. So yeah, I guess it would be a sentence. There exists, or there is. I like to say there exists though. And this one is for all. So the reason why it's called a quantifier is because we're quantifying some variable. We're saying something about the variable. So for example, here, this statement says, for all x, there exists a y. And the statement after that, there is a implied such that. So such that's kind of a weird part of a mathematical statement, or I guess logical statement like this. Because it's kind of like multiplication in some sense, because it's implied. You don't really write it, but it's there. So if there's no quantifier in between these 2 statements, like y and y is less than x, then there's a such then. So the way you would say this in words is, for all x, there exists a y such that y is less than x. Now here we're assuming x and y are real numbers. I didn't write that. And in fact, even if x and y are integers, this is true. For any integer you can think of, there is always some integer smaller. Like think of a random integer like 32. 30 is less than 32. Think of another random integer like negative 40. Negative 45 is less than negative 40. So for any integer you can think of, there exists one that is smaller. So this is definitely a true statement. Okay. Now we'll talk about these negations of these kind of quantifiers, where we have this p of x, which is technically an implicit quantifier, and p of x is just a statement involving x. It could be a statement like, y is less than x, but y is less than x actually doesn't work here because that would be a p of x comma y. So this is basically a function of x only. P reminds me of the phrase prime. So for example, this could be x is a prime. P of x could be x is a prime. You could have p of x being something else to do with x, like x is a square number, or x is even, or x is negative, something like that. So p of x is just some statement involving the number x. Okay? So this is not, or negating, the statement for all x such that p of x. So such that y is less than x, such that x is negative, such that x is even, whatever p of x means. Now this ends up being equivalent. So I'm going to write this equivalent statement, which is kind of like reminding me of an if and only if statement, or if and only if logical symbol. There exists x such that not p. Okay? So basically what happens is you can actually pass the negation through the quantifier, but the quantifier switches between for all and not, and there exists. Similarly, this statement is equivalent to for all x such that not p. So that's kind of interesting. Maybe we can talk about that with like an example, just saying it out loud. So let's say I'm negating the statement for all x such that x is even. That is saying there exists an x such that x is not even. Which is definitely true. I mean, it's kind of weird to think about it with that particular example. But yeah, you can try to think why those are equivalent exactly, and something to think about. And again, you can kind of write out any statement you want and try to play with it and see if it's true based on certain circumstances. And again, it depends what you want p of x to stand for. Maybe we can say p of x means x, like I said, is a prime number. So prime numbers, for example, are the numbers 2, 3, 5, 7, 11, 13. Any number that cannot be broken up further by multiplication besides 1 times itself. So let's take a look at the second one as an example. So let's say we're nodding the statement, there exists x such that p of x. So p of x meaning x is a prime. So there exists x such that x is a prime. That's what this statement says. And negating that means that there is not an x such that x is a prime. So what would that be equivalent to? So let's see. So there does not exist x such that x is a prime. Now, would that be equivalent to for all x is not a prime? That actually makes a lot of sense, because this is saying we're excluding a possibility of a prime, of x being a prime. So that if that's the case, then that means for any choice of x is not a prime. So again, something to think about. You can kind of play around with that idea. But anyways, that's where I wanted to end things for mathematical statements. So that concludes this video. So it's kind of not really too much has been spoken of here. It's not very, I mean, it's kind of deep, but we didn't really see too many crazy examples here. And I'll leave that for future topics where we'll be discussing more of this. So I thank you all for watching, and I'll see you in the next video.